Let's look at some things and try to figure out whether they're groups or not. So, what do we know so far? Well, we've had a couple examples, but let's bring in another number system. Uh, let's, let's, well, before we do that, let's just ask, are the integers under multiplication a group? Now remember, you could think of it as, can we always solve ax equals b using that method? What do we need in order to use that method? Well, the basic rules we would need are, we'd need to have an inverse. Every element would have to have an inverse. So, I mean, with the integers, some things have an inverse, right? If I have 1, I know 1 times 1 is equal to 1. And if I have -1, I know -1 times -1 is equal to 1. So we can sometimes get back to 1. If I have an equation like -1 times x equals 3, I can solve this in the integers. But once we start moving away from 1 and -1, it doesn't look good, right? If I wanted to solve 2x equals 3 in the integers, and I start off by looking for some element that I could multiply by to get rid of that 2, I'm not going to be able to find it. Similarly, I mean, we still have to worry about this, right? 0 doesn't have an inverse. It seems like the only things that have inverses are 1 and -1 in this situation. So this is definitely not a group. It would be associative, and it does have an identity. It meets two of the rules. It's associative because, well, multiplication is associative in the integers, in the rationals, in the reals. It doesn't matter. The way it's defined, it's associative. But we don't always have inverses, even though we do have a multiplicative identity. So this is not a group. Not a group. What if I wanted to do, say, I don't know, I'm going to make up a set. I'm going to just call it T. Don't get attached to this. It's just a single example. So this is going to be the multiples of 3. So the set of all 3x, where x is an integer. So the set of all the multiples of 3, and I want to know, is T under addition a group? Well, what do I want to do here? I want to look to see, is it associative? Well, yes, because it's a collection of integers, and the integers are associative. So if I take some of the integers and not all of them, addition's still going to be associative. You could even do the addition in the normal integers, and think of it as being taking place inside T. And by the way, you don't have to worry. If we add 2 elements of T, we end up back in T. This is an operation from T cross T. That takes us to T. So that would be checking for closure, checking that we stay in the system. But that's okay. So I only need to check my 3 rules. Does it have inverses? Well, let's think about it. Right? Is any multiple of 3, does that have an additive inverse? And the answer is yes, because if you take a multiple of 3, it's something of the form 3, let's not use x again, I'll say 3a. What would the inverse of 3a be? I need something that takes me to the identity, and the identity here would be 0, the additive identity. Well, minus 3a. But minus 3a is still a multiple of 3 because it's 3 times minus a. So we have inverses. We have the identity because 0 is a multiple of 3. What multiple? What would we have to multiply 3 by to get to 0? Well, 0. So we have an identity, we have inverses, and it's associative because because addition is associative. So this is a group, and we can solve equations in it. What would an equation here look like? Well, it would look like something like this. We'd have maybe 6 plus x equals -9 or something like that. And what would we do here? Well, I would find the inverse of 6, which is in T. It is in t. What is it? It's minus 6. And then I'd do this operation on the right, which is the hardest part of the problem. And then over here, I'd use the associative property. And the negative 6 and the 6 give me 0, which is a multiple of 3. So staying inside t, we are able to solve this equation and get our solution. So t is also a group. Notice that t under multiplication is not going to be a group. Now it is true that if you multiply two multiples of 3, you get a multiple of 3, because if you take 3a times 3b, that's equal to this, which is clearly, I don't need an equal sign there, which is clearly a multiple of 3. So since this is a multiple of 3, it's a binary operation that takes in two elements, spits out an element. We stay inside t, takes in elements of t, and it gives us elements of t. Multiplication would also be associative, but we have a few problems. Not only do we not have inverses, we don't have an identity under multiplication, right? So if we wanted to take this set t under multiplication, what would our identity be? We'd need something that we could take to say, hey, 3a times this identity has to be 3a for any a. The only e there that works is 1, but 1 is not in t. So we need an element outside of t if we want to map things back to themselves by multiplying. So this is not going to be a group, though t under addition is a group. So I guess before we look at the next video, maybe I'd like you guys to think about the even integers, the even integers with addition and multiplication. The odds, I don't like using O for anything to denote stuff because it looks like a 0. Odd integers. If it's not a group, ask yourself which rules it does satisfy and which it doesn't, right? Because the evens and odds are integers, and because addition and multiplication are associative in all integers, I can tell you right off the bat that all 4 of these are going to be associative. So ask yourself which are going to have an identity and which are going to have an inverse for every element. And you do need to also check, just to make sure, that the operation does send g cross g to g, in the sense that it does take in 2 inputs and give an output in the same place. So if you add 2 evens, do you get an even? If you multiply 2 evens, do you get an even? If you, I'm already giving away a little bit here. If you add 2 odds, what happens? Okay, well, I'll let you think about that. But we do need to move on because I want to talk about some very important groups soon. So think about maybe these 4 cases, and then we'll talk more in the next video.